Our universe holds secrets that break every law we think we know. You are about to discover 23 cosmic oddities that defy explanation and challenge our fundamental grasp of reality. By the end of this journey, you will see the cosmos through a completely new lens, understanding the profound mysteries that keep scientists awake at night. What force pulls entire galaxies toward the edge of the observable universe? Why does a star flicker in ways that no natural phenomenon can explain? These are not just curiosities. They are the frontier of human knowledge, each one a testament to a universe far stranger and more wonderful than we ever imagined. What does it truly mean to live in a reality where the rules are still being written? Deep within the constellation of Boötes lies a staggering emptiness, a region of space so vast it defies belief. This is the Boötes Void, a cosmic desert spanning an almost incomprehensible 250 million light-years. In a universe teeming with galaxies, this place is a profound nothing. If our Milky Way were at its center, we would not have known other galaxies existed until the 1960s. Cosmological models predict a relatively even sprinkling of matter across the cosmos, like seeds in soil, but the Boötes Void is a patch of barren ground on a continental scale. Astronomer Greg Aldering aptly called it a hole in the universe, a description that captures both its physical nature and its philosophical impact. How does such a void form? One possibility points to an incomplete understanding of dark matter, the invisible glue holding structures together. Perhaps its influence waned here, or the process of cosmic inflation stretched this pocket of space thin in its earliest moments. Alternatively, this could simply be a 1 in a billion statistical fluke, a cosmic lottery where one ticket holder gets nothing but empty space. The existence of the great nothing forces us to question a foundational principle, the assumption that the universe is largely the same everywhere when you look at the big picture. This immense patch of darkness is a silent challenge, a reminder that our maps of reality are still missing entire continents. And if one such void exists, what other immense structures or absences are waiting to be found? This immense cosmic desert is not the only structure that defies our expectations. Far beyond the emptiness of the Boötes Void, astronomers have detected a strange and relentless current, a mysterious motion they call dark flow. Entire clusters of galaxies are drifting in a coordinated direction, as if pulled by a force whose source lies beyond the edge of everything we can observe. This is not the random scattering of matter from the Big Bang. This is a purposeful stream, a cosmic river flowing toward an unknown destination. The discovery came from studying the faint afterglow of creation itself, the cosmic microwave background radiation. By mapping the subtle distortions in this ancient light as it passes through moving galaxy clusters, scientists led by cosmologist Alexander Kashlinsky found a pattern that should not exist. The clusters are all moving together on a scale so vast it challenges the very notion of a self-contained universe. Kashlinsky himself suggested this motion hints at a structure beyond the horizon of our universe. What could possibly exert such a gravitational pull? One staggering possibility is that our universe is just one bubble in a vast multiverse, and the gravity from a neighboring cosmos is tugging at us from outside our visible reality. Another theory points to conditions that existed before the Big Bang, remnants of a prior state of existence whose influence still echoes through the fabric of space. This dark flow implies that our cosmic home is not isolated, that we are connected to something far greater and more mysterious. It directly confronts the cosmological principle, the foundational idea that the universe is uniform and looks the same in all directions. If entire swaths of the cosmos are marching to the tune of an unseen conductor, then our origin story is profoundly incomplete. This mysterious current forces us to look outward, to wonder what immense forces operate on a scale we are only beginning to perceive. That mysterious current hints at forces beyond our sight, but it is not the only whisper from the dark. On a quiet August night in 1977, a radio telescope at Ohio State University heard a shout. For 72 seconds, a signal so powerful and so strange flooded its receiver that it overwhelmed the equipment. The data printout showed a string of letters and numbers so significant that the astronomer reviewing it, Jerry Amon, simply circled the sequence and wrote one word in the margin: "Wow." This was not the crackle of a distant star or the hum of a passing satellite. It was a narrowband radio signal, the kind theoretically produced by an artificial transmitter, and it came from the direction of the constellation Sagittarius. It was a perfect, fleeting cosmic hello that has never been heard again. For decades, scientists have searched for a repeat, scanning the same patch of sky with ever more sensitive instruments, but only silence has answered. The signal's unique properties make it difficult to explain with any known natural phenomenon. A comet was once proposed as the source, but its path did not align with the signal's origin. The possibility remains that it was a one-time transmission from an intelligence far away, a brief burst of a civilization saying, "We are here," before going quiet once more. Jerry Amon himself expressed doubt that a natural explanation could ever fully account for the signal's strength and focus. The WOW signal stands as a monument to the profound challenge of searching for extraterrestrial intelligence. It is the ultimate tease, a single data point that fuels both our deepest hopes and our greatest scientific frustrations. It forces us to wonder how many other such whispers have flashed in the cosmic dark, gone before we could even turn our heads to listen. While the WOW signal was a fleeting shout in the radio silence, another star has been communicating in a different, equally baffling language, the language of light. KIC 8462852, better known as Tabby's star, does not flicker like a normal star. It plunges into darkness. Observations from the Kepler Space Telescope revealed this star's light dimming in massive, irregular drops, sometimes by as much as 22%. This is not the gentle, periodic shadow of an orbiting planet. A planet would block maybe 1% of the light. This is as if a swarm of enormous, shapeless objects were passing in front of the star, blocking its light in a chaotic, unpredictable dance. When astrophysicist Tabitha Boyajian first brought this data to light, the scientific community was stunned. Nothing in our stellar playbooks could account for it. The immediate and most thrilling hypothesis was the possibility of alien megastructures, a vast array of energy-collecting panels orbiting the star, known as a Dyson swarm. Yet science must first exhaust the natural before embracing the extraordinary. Boyajian and other researchers proposed swarms of comets, immense clouds of interstellar dust, or the aftermath of a planetary collision. Each idea was investigated, and each fell short. The comet swarm theory could not explain the sheer depth and irregularity of the dimming. Dust would glow with infrared light, which was not observed in the expected amounts. This star is not just an anomaly. It is a direct challenge to our models of how stars and their planetary systems behave. It forces us to invent new physics, to consider exotic possibilities like a highly tilted dust ring or the spontaneous breaking up of a moon. The enduring mystery of Tabby's star demonstrates a profound truth. Sometimes the universe presents us with a puzzle not to test our existing knowledge, but to force us to create new knowledge. This single point of light, behaving so strangely, opens a door to phenomena we have not yet dared to imagine. phenomena that might be echoed in the bizarre life cycles of other, even more volatile stars. The strange behavior of distant stars finds a parallel much closer to home, in the form of a silent visitor from the depths of interstellar space. In 2017, a telescope in Hawaii detected an object hurtling past our sun, and it was immediately clear this was no ordinary comet or asteroid. It was the first confirmed traveler from another star system, and it was named Oumuamua, a Hawaiian word for scout or messenger. Its arrival was historic, but its properties were downright bizarre. This cosmic scout was unlike any rock in our own solar system. It had a highly elongated shape, perhaps 10 times longer than it was wide, tumbling through the void like a celestial cigar. The first true puzzle, however, was its motion. As it sped away from the sun, it accelerated in a way that gravity alone could not explain. Comets do this when sunlight vaporizes their ice, creating a jet of gas that acts like a tiny engine. But Oumuamua showed no coma, no tail, no visible sign of outgassing whatsoever. It was as if an invisible force was pushing it along. This non-gravitational acceleration set off a firestorm of debate. Harvard astronomer Avi Loeb offered a provocative explanation. He suggested Oumuamua could be a piece of advanced alien technology, a light sail propelled by the radiation pressure of starlight. Its flattened, pancake-like shape and its unexpected boost in speed were consistent with an artificial object, a discarded piece of a vessel or a deliberate probe. The scientific mainstream, of course, sought natural explanations. One compelling theory posits that Oumuamua was a chunk of solid nitrogen ice, a piece torn from a Pluto-like planet in a distant star system. As it passed close to our sun, the heat could have caused the nitrogen to sublimate, turning directly from a solid to a gas and providing the thrust, all without releasing the dusty debris that would make a visible tail. Yet even this elegant idea struggles to fully explain the object's extreme shape and reflectivity. Oumuamua challenges our very definitions. What is a comet? What is an asteroid? It appears to be something entirely new, a class of object that our solar system simply does not produce. Its brief flyby revealed that the building blocks of other planetary systems can be profoundly different from our own. This interstellar messenger is gone now, speeding back into the dark, but it leaves behind a profound legacy. It forced us to look up and acknowledge that our cosmic neighborhood is far more dynamic and diverse than we ever knew, with unknown objects silently drifting through the spaces between the stars. If one such scout has already passed through, how many more are out there, carrying secrets from worlds we can only dream of? The profound silence left by Oumuamua's departure echoes a much larger and more unsettling cosmic quiet, a puzzle so deep it bears the name of one of the 20th century's greatest minds. Enrico Fermi, during a casual lunch conversation in 1950, posed a question that has haunted science ever since. Where is everybody? The universe is ancient, nearly 14 billion years old, and unimaginably vast, with billions of planets orbiting in the habitable zones of their stars. The numbers alone suggest that life should have arisen countless times, with intelligent civilizations potentially saturating the galaxy. Yet when we train our telescopes on the heavens, we are met with a deafening silence. We hear no signals, see no visiting ships, and find no artifacts. This is the Fermi Paradox, the stark contradiction between the high probability of extraterrestrial life and the complete absence of any proof. Carl Sagan, a great believer in the abundance of life, also wrestled deeply with this silence. He and others have proposed the idea of great filters, catastrophes or challenges so immense that they prevent almost all life from progressing to the stars. Perhaps the filter lies in the past, in the incredibly difficult leap from non-living chemistry to the first self-replicating cell. Or maybe it awaits us in the future, a peril that every advanced civilization eventually faces, such as self-annihilation through war or environmental collapse. The silence of the cosmos could be a grim warning, a sign that no one makes it through the technological adolescence of a species. This paradox forces a humbling rethink of our place in the cosmos. Are we a lonely, early fluke, the first spark of consciousness in a young galaxy? Or are we simply not listening correctly, missing conversations that happen in ways we cannot yet comprehend? The unsettling quiet begs us to look deeper, to consider that the universe's greatest mysteries may not be its strange phenomena, but its profound and empty spaces. The profound silence of the cosmos is matched only by the profound darkness that structures it. We live in a universe where the matter we can see and touch, the stuff of stars, planets, and life itself, accounts for less than 20% of the total mass. The rest, the overwhelming majority, is an invisible presence known as dark matter. This is not merely empty space. It is a substance, a ghostly material that does not emit, absorb, or reflect any light, making it completely transparent to every telescope we have ever built. Its existence is felt only through its immense gravitational pull, a force so powerful it sculpts the very architecture of the cosmos. The story of its discovery begins with a brilliant and often cantankerous astronomer, Fritz Zwicky. In the 1930s, while studying the Coma cluster of galaxies, Zwicky noticed something deeply wrong. The individual galaxies were moving so fast that the cluster's own gravity should not have been strong enough to hold them together. According to all visible mass, the cluster should have flown apart long ago. Zwicky concluded there must be some form of dunkle materie, dark matter, providing the missing gravitational glue. For decades, his idea was largely ignored until the 1970s when astronomer Vera Rubin provided irrefutable evidence. By measuring the rotation speeds of stars within spiral galaxies, she found that stars on the outer edges were orbiting just as fast as those near the center. This defied the laws of gravity as we knew them. Imagine a merry-go-round where the children on the outer edge are whipping around at the same speed as those standing near the center. In our solar system, planets farther from the sun move more slowly, but in a galaxy, the stars are not slowing down, implying that an enormous, invisible halo of dark matter envelops each galaxy, its gravity spinning the stellar disk like an unseen hand. This dark matter is also the reason we can see some of the most distant objects in the universe. Its gravity acts as a colossal lens, bending the path of light from galaxies behind it, a phenomenon called gravitational lensing. We see multiple distorted images of the same galaxy, or brilliant rings of light, all tracing the outline of this invisible mass. For over half a century, physicists have been hunting for the particle responsible. They have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the rare, faint bump of a dark matter particle colliding with ordinary matter. Experiments with names like LUX and Xenon have listened intently, yet the silence from the depths has been as profound as the silence from the stars. What could this stuff be? The leading candidates are WIMP, or weakly interacting massive particles, hypothetical heavy particles that barely interact with normal matter. Another candidate is the ACTION, an ultra-light particle born from theories attempting to solve other puzzles in quantum physics. The continued failure to find these particles has forced a radical rethinking. Could our understanding of gravity itself be flawed on cosmic scales? Does dark matter even exist, or is it a symptom of our incomplete knowledge? This invisible architect, this ghost in the cosmic machine, is a humbling reminder that most of the universe is made of something we cannot see, cannot touch, and do not understand. It is the silent partner in the dance of the galaxies, a partner whose true nature remains just out of reach, pulling us deeper into the mystery of what holds our world together. If the ghostly pull of dark matter is not enough to unsettle you, consider the discovery of a force far more dominant and strange. The very fabric of space is not just expanding, it is accelerating, stretching apart at a rate that grows faster with every passing moment. This was not what anyone expected. For decades, cosmologists believed the mutual gravitational attraction of all matter in the cosmos would be applying a cosmic brake, gradually slowing the expansion that began with the Big Bang. The stunning truth, uncovered by two independent teams studying distant stellar explosions, was the exact opposite. By carefully observing a specific type of supernova, a reliable cosmic milepost, astronomers led by Saul Perlmutter found that these beacons were dimmer and therefore farther away than they should have been in a coasting or slowing universe. The only possible explanation was that something was actively pushing galaxies apart, a repulsive force that overwhelms gravity on the largest scales. This revelation was so profound it earned the teams the 2011 Nobel Prize in Physics. That something is what we now call dark energy, an enigmatic presence that makes up about 68% of the entire energy density of the cosmos. We cannot see it, trap it, or even properly define it, yet it dictates the ultimate fate of everything. What could it possibly be? The leading candidate is the cosmological constant, a form of energy inherent to the vacuum of space itself, a concept even Albert Einstein briefly entertained and then discarded as his greatest blunder. Perhaps empty space is not empty at all, but seething with virtual particles that pop in and out of existence, generating a gentle, relentless pressure that pushes the universe apart. Other theories suggest dark energy is a dynamic field, a fifth fundamental force that has evolved over cosmic time, its strength waxing or waning. The practical implication is a future that is both lonely and eternal. If dark energy continues to dominate, the expansion will accelerate without end. Distant galaxies will first fade from view as their light can no longer reach us. Then galaxy clusters will be torn apart, and eventually, even individual stars will be isolated in an ever-cooling, ever-darkening void. This is the heat death of the universe, a final state of profound stillness. The existence of dark energy is a direct challenge to Einstein's theory of general relativity, forcing physicists to ask if our understanding of gravity is fundamentally incomplete on cosmic scales. It is the ultimate cosmic oddity, a mysterious pressure in the void that is writing the final chapter of reality itself, a chapter we are only just beginning to read. Our own galaxy is caught in a cosmic current pulled by a force we cannot see. This is the Great Attractor, a gravitational anomaly of almost unimaginable power located in the direction of the constellation Centaurus. Our Milky Way, along with its entire local group of galaxies and the vast Virgo cluster, is rushing toward this point at a staggering 14 million miles per hour. The discovery of this motion in the 1970s revealed a profound imbalance in our cosmic neighborhood, a gravitational sink so immense it can tug on thousands of galaxies. The central mystery, however, is that its core lies directly behind the plane of our own galaxy, in a region astronomers call the zone of avoidance. This is a crowded and dusty part of the sky where the stars, gas, and dust of the Milky Way's disk block our visible light view, like trying to see a distant mountain through a thick forest. For decades, the heart of the Great Attractor remained a blur, its true nature hidden. Astronomers like René Cron-Courtoueg led the charge to see the unseeable. Using infrared and radio telescopes, instruments that can peer through the cosmic dust, her team began to map the hidden structures. They discovered that the Great Attractor is not a single, monstrous object. but likely the dense core of the Laniakea supercluster, a vast filament of 100,000 galaxies spanning 500 million light-years. Our own Milky Way resides on a suburban fringe of this immense cosmic metropolis, flowing downhill toward its gravitational center. Yet even this colossal supercluster may not fully account for the strength of the pull. The motion suggests there is more mass hidden behind the Great Attractor itself, an even larger structure pulling on the puller. This gravitational mystery forces a complete redrawing of our cosmic maps. We are not in a random, quiet part of the universe. We are passengers on a vast river of galaxies, flowing toward an unseen destination, reminding us that the largest forces shaping our cosmic journey often remain just out of sight. Even as we are pulled by the gravity of the Great Attractor, our planet is constantly bombarded by invisible projectiles from the depths of space. These are cosmic rays, not rays of light, but a hail of high-energy atomic nuclei and particles traveling at nearly the speed of light. They rain down upon our atmosphere in a silent, relentless shower, and some of them carry so much energy that their very existence seems to defy the laws of physics. The discovery of this invisible rain began with a series of daring balloon flights by physicist Victor Hess in 1912. He found that electroscopes, instruments that measure electric charge, discharged more quickly the higher his balloon ascended. This proved the ionizing radiation was coming from above, from space itself, and not from the ground, a revelation that earned him the Nobel Prize. But the modern mystery lies with the ultra-high energy cosmic rays, particles with energies beyond 10 to the power of 20 electron volts. To grasp that scale, a single one of these subatomic particles carries the kinetic energy of a professionally thrown baseball, all packed into a speck smaller than an atom. According to our best models, such particles should not be able to travel across intergalactic space. The universe is filled with the faint glow of the cosmic microwave background radiation, the leftover heat from the Big Bang, and these photons should act like a thick fog, robbing ultra-high energy particles of their momentum over long distances. The fact that they reach us at all, intact and with their phenomenal energy, means they must come from relatively nearby sources within our local supercluster of galaxies, and they must have been accelerated by something unimaginably powerful. Giant facilities like the Pierre Auger Observatory in Argentina track these rare events. It spans an area the size of Rhode Island, with 1,600 water tanks that detect the faint flashes of light produced when a cosmic ray slams into the atmosphere, creating a vast cascade of secondary particles. By tracing the paths of these particle showers back into the sky, astronomers hunt for the sources. Some point to cataclysmic events like active galactic nuclei, where supermassive black holes devour matter and blast out jets of energy, or to the collapsing cores of massive stars in gamma-ray bursts. Yet for many of the most energetic rays, the map leads to empty space, to voids between galaxies where no known engine resides. This is the core of the oddity. We are detecting cosmic bullets fired from a cosmic gun we cannot find, forcing us to question our understanding of particle acceleration and the strength of magnetic fields that may bend their paths. It suggests there are colossal, transient events in the cosmos, eruptions of power we have not yet witnessed, capable of launching matter with a force that dwarfs our largest particle colliders. The mystery of these unidentified high-energy particles is a humbling reminder that even from the void, the universe is actively, violently, and mysteriously communicating with us. Even the most meticulously planned journeys can hold hidden surprises. As the Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt, they carried with them a golden plaque, a message to any potential finder about the species that built them. But the spacecraft themselves were sending back a different, more perplexing message. A tiny, unexplained force was acting upon them, a constant sunward deceleration so slight it was barely measurable, yet it persisted for years. This was the Pioneer Anomaly. For decades, this subtle drag confounded physicists. The probes were on a precise trajectory to escape the solar system, yet something was ever so gently tapping the brakes. The force was minuscule, comparable to the weight of a single grain of sand pressing on the spacecraft. But in the pristine vacuum of space, where every action is predictable, this was a glaring inconsistency. It was as if an unseen hand was reaching out, pulling them back. Teams of scientists, like the one led by John Anderson at NASA, a jet propulsion laboratory, wrestled with the data. Could this be the first crack in Einstein's theory of general relativity? Was there some unknown property of gravity that only revealed itself in the vast, empty stretches between planets? Perhaps dark matter was collecting around the solar system, exerting a faint additional pull. The anomaly became a classic scientific detective story, a puzzle that forced a re-examination of our most fundamental laws. The resolution, when it finally came, was a masterclass in humility. After years of painstaking analysis, the culprit was identified not as new physics, but as old physics in a place no one had fully appreciated. The spacecraft were powered by radioactive plutonium, and the heat from that decay was emitted by the onboard electronics. This thermal radiation was not perfectly symmetrical. A tiny fraction more heat was radiating from the back of the spacecraft's main antenna dish than from the front. This imbalance created a photon thrust, a gentle but constant pushback toward the sun. It was the spacecraft's own warmth slowly pushing them off course. The Pioneer Anomaly serves as a profound cautionary tale. It reminds us that in the quest for monumental discoveries, we must first account for every mundane possibility. It highlights the incredible precision of modern physics, where the faint glow of warmth from a nuclear battery can mimic the signature of a revolutionary new force. This lesson in meticulousness now guides our approach to other, more modern precision anomalies, teaching us to listen carefully to the whispers of the cosmos, for they often speak of things we have overlooked in our own backyard. The silent rain of cosmic rays is punctuated by flashes of light so brief you would miss them in a blink, yet so powerful they outshine entire galaxies. These are fast radio bursts, the universe's most enigmatic Morse code. They arrive without warning, a blast of radio waves that compresses the energy output of our sun over 3 days into a pulse lasting just a few thousandths of a second. The first was discovered in 2007, buried in archival data from a radio telescope in Australia. A single spike of intensity so extraordinary that astronomer Duncan Lorimer initially thought it was an error. But it was real, a shout from a galaxy billions of light years away. The central mystery is the engine behind these flashes. What natural phenomenon can be both instantaneous and unimaginably violent? The prime suspects are magnetars, a type of neutron star with a magnetic field so intense it could strip the information from a credit card from half the distance to the moon. A starquake on such an object could theoretically snap its magnetic fields, releasing a firestorm of radio waves in a single, catastrophic crack. Other theories point to the final, fatal mergers of neutron stars or the evaporation of primordial black holes. Yet one discovery made these explanations far more complicated. Some of these bursts repeat. FRB 1211-2, for instance, fires off signals again and again, not randomly, but sometimes in a discernible pattern. This simple fact rules out any model based on a single cataclysmic explosion. You cannot blow up the same star twice. The repeating bursts suggest a source that survives its own outburst, like a lashing magnetic whip or a pulsar orbiting through a thick cloud of gas. The very brevity of these events is a clue in itself. Because the burst is so short, the object creating it must be physically small, likely no larger than a few hundred miles across, ruling out giant stars or vast nebulae. As these fleeting signals race across the universe, they also serve as cosmic probes. The different frequencies within a single burst get stretched and delayed as they pass through the sparse gas between galaxies, allowing astronomers to literally weigh the missing ordinary matter in the cosmos. These millisecond flashes are not just cosmic oddities. They are both messengers and mysteries, pointing to a universe teeming with violent, transient events that we are only now learning to see. What other fleeting phenomena flicker in the darkness, their stories told in bursts too quick for the human mind to comprehend? Even the faint afterglow of creation holds a potential crack in our cosmic worldview. The cosmic microwave background radiation is the oldest light we can see, a baby picture of the universe taken just 380,000 years after the Big Bang. According to our most cherished principles, this radiation should be a perfectly even tapestry, a uniform glow showing no preferred direction. Yet some cosmologists claim to see a ghostly alignment imprinted upon it, a pattern so unsettling it was dubbed the axis of evil. The name, coined by cosmologist Kate Land, reflects just how problematic this finding would be if proven true. It suggests the universe has a preferred axis, a cosmic north that breaks the foundational rule of isotropy, the idea that the universe looks the same in all directions. This axis is not a physical structure but a statistical preference in the temperature fluctuations of the ancient light, a whispering suggestion that one direction is somehow different from all others. The implications are staggering. If the universe has a handedness, a preferred alignment, it could point to influences from before the Big Bang, relics of a prior state of existence that imprinted their structure on our own. Alternatively, it could reveal a fundamental flaw in our theory of cosmic inflation, the period of unimaginably rapid expansion that is supposed to have smoothed the universe into uniformity. Perhaps inflation was not perfectly symmetric, leaving behind a subtle warp in the fabric of reality. Skeptics argue forcefully that the axis of evil is likely an illusion, a combination of statistical noise and contamination from our own galactic neighborhood. The dust and magnetic fields of the Milky Way could be creating a foreground signal that we have not yet perfectly subtracted from the data. Yet this controversial pattern has proven stubborn, persisting through multiple data sets from different space telescopes. It refuses to be wiped away completely, keeping a vital scientific debate alive. This potential alignment forces a profound re-examination of our most basic cosmic assumptions, challenging us to consider that the universe may not be as random and directionless as we once believed. The whispers from this ancient light lead us to other, equally strange anomalies hidden within the cosmic microwave background itself. These fleeting flashes of radio energy are chaotic and unpredictable, but a more fundamental paradox lies at the very edge of spacetime itself. When matter is pulled into a black hole, it passes the point of no return, the event horizon, and is seemingly erased from the universe. According to Einstein's general relativity, the black hole's gravity is so absolute that nothing, not even light, can escape. All the intricate information about that matter, its atomic structure, its history, everything that made it what it was, is crushed into the singularity and lost forever. But this creates a direct conflict with the other pillar of modern physics, quantum mechanics. Quantum mechanics insists that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must be preserved in some form. This is the principle of unitarity, a foundational rule of the quantum world. The complete and permanent loss of information into a black hole shatters this rule, creating the black hole information paradox. Stephen Hawking famously highlighted this problem, arguing that black holes do indeed destroy information. His own discovery, Hawking radiation, only deepened the mystery. Quantum effects at the event horizon cause a black hole to slowly leak energy, evaporating over trillions of years. If the black hole vanishes, what happened to all the information about the stars, planets, and particles it consumed? The universe would be left with a final state of bland radiation, a thermal haze with no memory of its past, a clear violation of quantum law. This is not a minor technicality. It is a battle for the soul of physics, forcing a choice between our two most successful theories. To resolve the paradox, physicists have been driven to radical ideas. One leading proposal is the holographic principle, which suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its surface, the event horizon, like a cosmic fingerprint smeared across a two-dimensional screen. The three-dimensional world we experience inside could be a projection from this two-dimensional data. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth gateway, but a blazing wall of high-energy particles. Any object crossing it would be instantly incinerated, preserving information at the boundary by preventing it from ever truly entering the black hole in the first place. Yet this idea itself contradicts the principle of equivalence from general relativity, which states that an observer falling into a black hole should notice nothing special at the event horizon. We are left with a dizzying puzzle where every solution seems to break a fundamental law. The information paradox is more than a theoretical argument. It is a direct probe into the nature of reality, asking what space-time is at its most fundamental level and whether our universe is, at its heart, predictable and orderly. The struggle to understand what black holes truly do with our past forces us to look for clues in the very fabric of the cosmos, leading to other quantum enigmas that are equally strange. At the far edge of our solar system, the orderly disk of icy worlds simply stops. This is the Kuiper Cliff, an astronomical mystery where the ring of debris beyond Neptune plunges into an unexpected void. Astronomers call this region the Kuiper Belt, a frozen reservoir of primordial material left over from the solar system's birth. Models predict it should extend for hundreds of astronomical units, with the number of objects gradually thinning out like a fading echo. Instead, at about 50 times the Earth-Sun distance, the population of these icy bodies drops off a cliff. It is as if you were walking through a forest that abruptly ends at a sharp, unnatural edge, with nothing but empty plains beyond. This sudden depletion defies every simulation of how planetary systems form. The primordial disk of gas and dust that swirled around our infant sun should have left a much more extensive and populous belt of icy planetesimals in its wake. The sheer abruptness of the cliff points to a dramatic intervention, a cosmic event that swept this outer realm clean. One compelling hypothesis suggests a close encounter with another star in our sun's early history, a stellar flyby whose gravity plucked away the outer members of this frozen family like a passing hand scattering dust. Another, even more tantalizing idea involves an unseen shepherd, the gravitational influence of a hidden planet, a so-called Planet 9, could be responsible for carving this sharp boundary. This hypothetical world, several times the mass of Earth on a wildly elongated orbit, might have gathered the outer Kuiper belt objects into a tight cluster, clearing out the vast region beyond through its immense gravitational pull. Observations from the Hubble Space Telescope and other powerful instruments have consistently confirmed this strange emptiness, fueling an ongoing hunt for the perturbing body that might be responsible. The Kuiper Cliff is more than a curiosity. It reshapes our entire understanding of the solar system's final frontier, suggesting that our home is not a perfectly preserved relic but a dynamic system whose history may include stellar encounters or hidden, massive worlds. This sharp edge in our own cosmic backyard forces us to look with fresh eyes at the very boundaries that define our place in space. This fundamental disagreement over the universe's expansion rate is one of the most pressing crises in modern cosmology. The Hubble constant, a number representing how fast the cosmos is stretching, should be a single, universal truth. Yet when we measure it using two different, trusted methods, they give us different answers. It is a cosmic rift, a discrepancy known as the Hubble Tension. On one side, we have the ancient light of the cosmic microwave background, meticulously mapped by the Planck satellite. This fossil from the infant universe allows us to predict, based on the standard model of cosmology, what the expansion rate should be today. That prediction is about 67 kilometers per second per megaparsec. On the other side, we have local measurements that look at relatively nearby stars and supernova. These observations, which include work by astronomers like Wendy Friedman, consistently find a faster rate around 73. A difference of 6 may seem small, but the statistical certainty of both results means this gap is real and significant. It is not a simple error. It is a stubborn inconsistency that refuses to go away. This tension forces us to ask a profound question. Is our standard model of the universe, the very foundation of modern cosmology, missing a crucial ingredient? One compelling possibility is an early form of dark energy that briefly surged and then faded in the universe's first moments. This extra push would have altered the initial conditions, changing the Planck prediction to better match what we see locally. Other theories suggest that dark matter might have properties we do not yet understand, or that our cosmic distance ladder, the sequence of methods we use to measure vast distances, has a hidden rung that is slightly off. The implications are staggering. The Hubble constant is not just a number. It is used to calculate the age of the universe, its size, and its ultimate fate. A faster expansion rate implies a younger and perhaps differently evolving cosmos. Resolving this tension is not about finding which team is right. It is about discovering what we have all been missing, a new piece of physics that operates on the grandest of scales. This fundamental disagreement echoes the deep challenges of measuring the cosmos, a problem that becomes even more apparent when we look at the very glue holding it all together. We can map the stars and galaxies with astonishing precision, yet a simple cosmic inventory reveals a startling shortfall. According to our most trusted models of the Big Bang, there should be a certain amount of ordinary matter in the universe, the baryons that make up every star, planet, and speck of dust. But when astronomers add up everything they can actually see, they come up short. Nearly half of all the normal matter in the cosmos is simply missing. This is not the mysterious dark matter. This is the very stuff we are made of, and it has seemingly vanished. The hunt for these lost baryons is one of cosmology's greatest detective stories. Prime suspect is not a hidden object, but a hidden state of matter. Theorists believe the missing material is woven through the voids of space in a diffuse cosmic web, a network of faint filaments of incredibly hot, ionized gas stretching between galaxies. This warm, hot intergalactic medium is so tenuous and so scorching that it does not glow brightly in any single wavelength. It is a ghostly haze, a cosmic fog that has eluded our telescopes for decades. The European Space Agency's XMM Newton Observatory has made inroads, detecting the faint X-ray glow of this gas in the densest filaments of the cosmic web, like finding the first few threads of a vast, invisible tapestry. But this accounts for only a fraction of the total. The rest remains at large, a pervasive presence we know must be there, yet cannot fully grasp. This missing matter puzzle forces a critical rethink of how galaxies form and evolve. These baryons are the raw fuel for star formation, the reservoir from which future generations of stars are born. If this material is hiding in plain sight, spread thinly across the immense voids, our simulations of cosmic evolution are missing a crucial ingredient. The search is now turning to a new generation of instruments, telescopes that can probe the soft X-ray and ultraviolet signatures of this ultra-diffuse gas. Finding this lost half of the ordinary universe is more than an accounting exercise. It is about completing our picture of the cosmic ecosystem, understanding where the fundamental building blocks of reality have chosen to reside. This composition mystery leads us directly to another, one that strikes at the very heart of matter itself. The very laws of physics seem to forbid their existence, yet they arrive all the same. These are cosmic rays carrying so much power that they should have been bled dry by the cold emptiness of space long before they ever reached us. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin calculated a fundamental speed limit for particles traveling across the universe. They realized that space is not a perfect vacuum. It is filled with the faint afterglow of the Big Bang, a sea of low-energy photons known as the cosmic microwave background. A proton traveling at near light speed with an energy above a certain threshold should smash into these background photons. From our perspective, that gentle background glow would appear as a storm of high-energy gamma rays to the ultra-fast proton. The collision would be catastrophic, creating a shower of new particles and sapping the proton's energy over a relatively short cosmic distance. This is the GZK Cutoff, a theoretical wall that should make it impossible for us to detect these ultra-high energy particles from sources more than a few 100 million light-years away. The universe itself should be shielding us from them, but it is not. Experiments like the telescope array in Utah have repeatedly recorded cosmic rays with energies far beyond this supposed limit. These are not just minor violations. They are particles arriving with energies millions of times greater than anything produced in our largest particle colliders, and they appear to come from all directions, including voids of empty space where no known cosmic engine exists. This violation is a direct challenge to our understanding of special relativity and particle physics. How did these particles cheat the cosmic friction? One possibility is that their sources are much closer than we think, hidden cosmic powerhouses within our local supercluster of galaxies, perhaps nearby active galactic nuclei with their supermassive black holes, are acting as natural particle accelerators of unimaginable scale. Another, more exotic idea points to the decay of super-heavy dark matter, hypothetical particles left over from the Big Bang that are billions of times more massive than a proton. The spontaneous disintegration of just one of these primordial relics could release the energy we observe. Each of these detected particles is a messenger from the extreme frontiers of physics, telling us that our models of particle acceleration in the universe are incomplete. They force us to consider that the emptiest parts of space might be crackling with energies and processes we have yet to dream of, pointing toward other phenomena where the very fabric of reality is tested. The very elements forged in the first moments of creation carry a secret, a mismatch written into the fabric of ancient stars. According to our most precise models of the Big Bang, the universe in its first few minutes was a nuclear furnace, fusing protons and neutrons into the lightest elements. This process, known as Big Bang nucleosynthesis, produced precise amounts of hydrogen, helium, and a tiny trace of lithium. The calculations are elegant, and for hydrogen and helium, the predicted abundances match what we observe in the oldest regions of the cosmos almost perfectly. But for one element, the numbers are starkly wrong. The theory states that there should be about 3 times more lithium-7 in these primordial stars than we can actually find. This is the cosmological lithium problem, a quiet but persistent crack in the foundation of our origin story. Pioneers like David Schramm helped solidify these predictions, yet when astronomers measure the lithium in the atmospheres of ancient stars, the data consistently comes up short. It is as if someone went through the early universe and secretly removed 2 out of every 3 lithium atoms. Where did they go? One possibility is that our understanding of nuclear physics is incomplete. Perhaps there were unknown nuclear reactions in the primordial soup, pathways that destroyed lithium as quickly as it formed. Another line of thought points to the stars themselves. Maybe these ancient suns are not pristine containers. They could have internal processes that slowly drag lithium down from their surfaces into their hot interiors, where it is destroyed, effectively hiding the evidence from our telescopes. This tiny deficit forces a monumental question. Is our standard model of cosmology, which works so beautifully on the grandest scales, missing a crucial piece when applied to the universe's first few minutes? The lithium problem is a whisper from the dawn of time, suggesting that the recipe for our cosmic beginnings might need a subtle but important revision. This elemental anomaly invites us to look for other cracks in our understanding, other places where the universe's composition defies our expectations. The heart of our own galaxy is speaking in a language of pure energy, a whisper of gamma rays that defies all explanation. For years, the Fermi Gamma Ray Space Telescope has been mapping the sky in the most energetic form of light, and its data revealed something strange blooming from the galactic center. This is not the gentle glow of starlight, but a fierce, unexplained excess of gamma radiation. Its spatial pattern and its specific energy signature do not match any known population of celestial objects. It is not the predictable pulse of spinning pulsars, nor the chaotic spray from cosmic ray collisions. This glow is something else entirely, a phantom signal from the darkness. When astrophysicists like Tracy Slatire and her team analyzed this excess, they found its properties were tantalizingly consistent with a long-sought-after dream, the annihilation of dark matter. The idea is that dark matter particles drawn into the galaxy's immense gravitational well could be colliding with their antimatter counterparts. When matter meets antimatter, they annihilate in a flash of energy, and for certain types of hypothetical dark matter particles, that flash would be a burst of gamma rays precisely matching the observed glow. It is a ghost potentially revealing itself by its own destruction, yet the universe rarely offers simple answers. This same signal could also be produced by a dense, unseen crowd of millisecond pulsars, the rapidly spinning corpses of dead stars, or by past outbursts from the supermassive black hole, Sagittarius A star. The challenge is that we cannot simply point a telescope and see which one it is. We are listening to a chorus of voices and trying to pick out a single singer. This galactic center excess is a perfect representation of the frontier in indirect dark matter detection, a field where every potential discovery is shrouded in astrophysical fog. It forces us to ask whether we are seeing the first faint signal of the universe's dominant matter, or if we are merely discovering a new class of celestial object we never knew existed. This enigmatic glow from our galaxy's core is a beacon pointing toward other profound mysteries hidden in the same turbulent region. That same galactic core, a crucible of violent energy, also gives rise to structures of impossible elegance. Far from the chaos in the constellation Monoceros lies a dying star that has painted its own funeral shroud with geometric perfection. This is the Red Rectangle Nebula, a cosmic artwork that defies the very nature of stellar death. Most nebulae are chaotic and formless, great clouds of gas blown into irregular shapes by stellar winds. But this one is different. It presents itself as a near-perfect rectangle, a frame of glowing red gas with a series of concentric rungs, like a ladder leading into the heart of darkness. At its center, a pair of aging stars locked in a tight dance hold the brushes. The prevailing theory suggests that as one of these stars began to shed its outer layers, the powerful gravitational influence of its companion star funneled that expelled material into two opposing cones. From our vantage point, we look directly down the barrel of this double cone, its edges creating the sharp, rectangular illusion. The stunning concentric rings, however, add a deeper layer of mystery. They are not solid structures, but waves of material like ripples in a pond, ejected in precise pulses every few hundred years. The Hubble Space Telescope has provided our clearest view of this phenomenon, resolving the delicate latticework of dust and gas. Each ring is a fossil record, a timestamp of a violent episode where the star coughed a shell of matter into space. The profound symmetry forces us to question what natural process can create such regularity. It is a natural clockwork, a celestial metronome ticking to a rhythm we do not yet fully hear. The red rectangle is more than a pretty picture. It is a laboratory for understanding the final, delicate breaths of sun-like stars, showing that even in death, the universe can express itself with an artist's precision. This drive to find order in the cosmos leads our search to the most fundamental level of all, to the particles that should not exist. Deep within the heart of an atom, the rules are being rewritten. The tetraneutron is a phantom, a hypothetical particle that should not exist. It is a cluster of 4 neutrons bound together without a single proton to hold them. According to our most robust models of nuclear physics, this configuration is impossible. The strong nuclear force, the very glue that binds atomic nuclei, should not be able to hold 4 neutral particles together. Such a state is predicted to be unbound, decaying into separate neutrons in an instant, a fleeting spark too brief to ever be seen. Yet, experiments have suggested otherwise. At facilities like the Riken Research Institute in Japan, scientists have fired beams of helium-8 nuclei at targets and observed the debris. The data hinted at a resonance, a brief, stable state of 4 neutrons appearing for just 1/1000,000,000th of a second before vanishing. This is not a direct observation, but a ghost in the data, a statistical whisper that has ignited a firestorm of debate. If this tetraneutron is real, it forces a radical overhaul of our understanding of the strong force. We would have to accept that neutrons can form stable, proton-less matter under conditions we never anticipated. This has staggering implications for the most extreme objects in the cosmos. The cores of neutron stars are vast seas of neutron-rich matter, and the existence of tetraneutrons could fundamentally alter our models of their density and behavior. It suggests that in the crushing pressures at the heart of these stellar corpses, matter could be organizing itself in ways we have not yet dreamed of. This subatomic phantom is a direct challenge, a tiny key that could unlock vast cosmic doors, pushing us to question what other fundamental particles are hiding in plain sight, waiting to be discovered. Even the oldest light in the universe holds a cold and silent secret. Among the subtle warm and cool spots of the cosmic microwave background, one region stands out for its profound and unsettling chill. This is the cold spot, a vast and inexplicably cool area in the constellation Eridanus, discovered by the Wilkinson Microwave Anisotropy Probe satellite. It is not just a little cold, it is significantly colder and far larger than our best models of cosmic inflation can easily explain. This is not a simple statistical fluke, but a cosmic bruise on the face of the sky, a patch of shadow that challenges our understanding of the universe's very first moments. To grasp its scale, if you could see this cold spot with your naked eyes, it would appear several times larger than the full moon, a gap in the ancient glow that speaks of a deep emptiness or something far stranger. One compelling theory suggests this chill is caused by a supervoid, an immense and mostly empty region of space lying between us and the cold spot. As light from the cosmic microwave background travels through such a void, it must climb out of a gravitational well, losing energy and stretching to longer, cooler wavelengths in a process known as the integrated Sachs-Wolf effect. Yet, when astronomers went searching for this proposed void, the structures they found did not seem nearly large or empty enough to account for the profound cold we observe. The numbers simply do not add up, leaving a gap in the explanation as vast as the cold spot itself. This failure has led to a more staggering possibility, one that pushes the boundaries of cosmology itself. Perhaps the cold spot is not a feature of our universe at all, but the scar of a collision with another universe in the vast multiverse. In this theory, the cosmic inflation that created our universe was not a unique event, but one of countless bubble universes constantly forming and expanding. If our bubble had brushed against another in the first instance of time, the energy of that collision could have left a permanent mark on our cosmic background, a cold imprint where the fabric of reality was fundamentally altered. This idea transforms the cold spot from a mere anomaly into a potential window into the multiverse, a glimpse of a cosmos beyond our own. Of course, many scientists maintain a more conservative view, arguing that we are simply seeing a rare but natural statistical fluctuation, a 1 in 1,000 chance that just happened to occur in our observable sky. The Planck satellite has studied this region with exquisite detail, and while it confirmed the cold spot's existence, it could not definitively rule out this possibility of a cosmic coincidence. The debate continues, a quiet but persistent hum in the background of cosmological research. This chilly patch forces us to confront the limits of our knowledge. It tests the principle of uniformity that underpins our entire cosmic model, suggesting that the infant universe may have been less even, less predictable than we have long assumed. As we reflect on these 23 cosmic oddities, from the great nothing of the Boötes Void to this final cold whisper from creation, a profound pattern emerges. The universe is not simply a place of known laws and orderly progression. It is a realm of profound mystery, where the rules are constantly being challenged and rewritten. Each of these puzzles, from dark flow to the information paradox, is a gift, a beacon pointing toward a deeper, stranger, and more wonderful reality waiting to be understood. The greatest discovery is not a single answer, but the beautiful, humbling realization of how much we have yet to learn. Galileo's first glimpse of Jupiter's moons through his primitive telescope shattered a 2,000-year-old belief that everything revolved around the Earth. Each generation since has wielded new tools that revealed a universe far grander and more mysterious than the last. Edwin Hubble's discovery that distant galaxies are rushing away from us unveiled an expanding cosmos, a reality no one had previously dared to conceive. The recent detection of thousands of exoplanets, worlds orbiting distant suns, transformed our solar system from a unique sanctuary into one of billions. Every single one of these breakthroughs began as an anomaly, a piece of data that did not fit the established picture. The cosmic oddities we grapple with today are not signs of failure. They are the very engine of scientific revolution. They represent the frontier where our current models strain and crack, forcing the birth of new ideas. This long arc of discovery teaches a profound lesson in humility. Our current understanding of the universe, for all its mathematical elegance, is almost certainly incomplete, a temporary sketch awaiting revision by the next generation of curious minds. The greatest discoveries lie not in confirming what we already know, but in stumbling upon the phenomena we cannot yet explain. These 23 cosmic oddities are not failures of our science. They are its ultimate purpose, from the immense silence of the Boötes Void to the chilling whisper of the cosmic cold spot. Each mystery is a signpost pointing toward a deeper reality we have only begun to explore. They challenge every law we think is fixed, proving that our current understanding is a temporary sketch, not a finished masterpiece. The true value of these puzzles is not in the answers we have, but in the questions they force us to ask. They invite us to push the boundaries of knowledge, to invent new physics, and to see the universe not as a static collection of facts, but as a living, evolving story that we are helping to write. This relentless curiosity is our greatest tool, the engine that has driven every discovery from Galileo's telescope to the Webb Space Telescope. Carl Sagan's words ring truer now than ever before. Somewhere, something incredible is waiting to be known. It might be hidden in the flicker of a distant star, encoded in a millisecond radio burst, or woven into the fabric of dark matter itself. Let these cosmic oddities reignite your own sense of wonder. The next time you look up at the night sky, remember that you are gazing into a canvas of profound mystery. We want to know which of these 23 oddities captured your imagination the most. Was it the silent pull of the Great Attractor, the bizarre cigar shape of Oumuamua, or the existential dread of the Fermi Paradox? Share your thoughts in the comments below, and if this journey into the unknown has left you wanting more, subscribe for our next exploration. The cosmos holds endless secrets, and the next great revelation is waiting just beyond the edge of our vision.